the explosive, thrillingly awesome power of tech. That's what inspires us. So no matter what the future holds, we're ready to bring on tomorrow.
Okay, welcome back. If everybody can grab their seats, or if you want to stand, that's fine too. I know I need to stand upon occasion, so we welcome you back on this one. We have another great panel coming up here called Supporting Space Sustainability, the Future of ISAM. So we've put together a real great panel here. This session, as you just saw, is brought to you by SAIC. We thank them again for their sponsorship of this particular panel and the panels today. Let's welcome Ezinne Uzo-Okoro. Got it. I got her first name right, which is awesome. We were talking out in the hallway, and I said, okay, it's Ezinne, right? And she's like, yeah, it's French. And I said, okay, well, I don't see an aigu at the end of the E. And she says, well, there is one. And I said, well, I don't see it. It's not on my paper. So, but she is the Assistant Director for Space Policy at the White House Office of Science and Technology. Real fun person, I can tell just from our conversation. And welcome. And please introduce your panel, and we can move on. Thank you.
Good morning to you all. So I'm Ezinne Uzo-Okoro, and I'll just briefly introduce the White House Office of Science and Technology Policy before I introduce my esteemed panelists here. So the White House Office of Science and Technology Policy advises the President and all policy councils within the Executive Office of the President on all matters of scientific engineering and technical aspects of the economy, national security, health, homeland security, foreign relations, the environment, amongst a number of other topics. We also coordinate the entire U.S. government on science and technology efforts, and we lead, together with the Office of Management and Budget, an annual review and analysis of federal research and development budgets across the entire agency. Now, my role there is one of leading the civil and commercial space portfolio, which includes Earth observations, orbital debris, planetary protection, aeronautics, microgravity, and today's topic, which is in space servicing, assembly, and manufacturing. There is an interagency working group that was started about 10 months ago now to really look into what we could do to help elevate this new era of servicing, assembly, and manufacturing. It used to be called On Orbit, servicing, assembly, and manufacturing, but we believe that these technologies and suite of capabilities are necessary for multiple orbital regimes in space. And so we developed an ISAM national strategy, and I look forward to talking to the panelists about them, but we'll start with introductions. Jeremy, you want to go ahead?
Hello, everyone. My name is Jeremy Schiel. I'm the co-founder and chief development officer of OrbitFab, and we are gas stations in space. So we're putting up a network of propellant depots for storable propellants only, not cryogenics, to essentially provide that refueling needs for the ISAM industry. So we actually developed the RAFTI, the Rapidly Attachable Fluid Transfer Interface, in combination with about 50 international organizations and government agencies gathering requirements along every step of the way to make sure that as we're developing this fueling port, it's something that the industry wants, not what we think the industry wants. So we've worked with organizations like AFRL, SSC, UK MOD, as well as JAXA and a bunch of other companies and organizations. We have the first fuel depot that we launched last June, which is in Sunsync, carrying high-test peroxide, which is our stepping stone to offering hydrazine and xenon, which are the two most used propellants in the industry. The big thing is we talk about a sustainable space and wanting a sustainable industry, but we still are living in a disposable industry where you build something, you put the fuel in, once the fuel runs out, you throw it away, even when more than 80% of the time the technology is still used and can be used for either developing countries or other mission sets. So we talk about sustainable industry. In order for that to happen, we really need to focus on refueling first.
Thank you. Our next panelist is Karl Stolleis.
So my name's Karl Stolleis. I have been the program manager for space logistics and robotics at AFRL in Albuquerque for the last couple of years. And everybody on the panel here are folks that I have known for any number of years, and I've really enjoyed working with them on this whole topic. With the stand-up of the Space Force a couple of years ago, I think everybody saw, or if you haven't seen, the Space Power Doctrine document that came out. It was the first time that space mobility and logistics was listed as a core competency in space for the Department of Defense. And we've been spending a lot of time with both industry and NASA and other government agencies trying to understand how DoD needs to implement that strategy. And I think one of the things that's really exciting and key to me is, so Jeremy is working on refueling. Al and the folks at Redwire are stepping into the assembly and the manufacturing. I mean, this is a really exciting time. And as trite and cliche as it sounds when it comes out of my mouth, this is a paradigm shift in how space will be done. This is a different way of operating in space. And the technologies aren't new, the ideas aren't new. I mean, some of the Werner von Braun crowd in the 50s was talking about satellite servicing and refueling. So this is not a new idea. The difference is, I think, with the new technologies and capabilities that we have coming online, there is the opportunity to make this real. And I think the folks sitting here at this table are some of the folks that can make it happen. But it's going to take all of us doing it. So.
Thank you, Karl. Our next panelist is CTO of Redwire, Al Tadros.
Good morning. Excited to be here. I'm Al Tadros, Chief Technology Officer at Redwire. If you haven't heard of Redwire, that's because we were formed and grew in the last 2 years while everybody was in a pandemic. We grew out of the acquisition of 8 companies, and 3 of which have been very central and focused on the ISAM technologies and expansion, and that includes Made in Space, TechShot, and our deployable space solutions team in Goleta. Very exciting set of technologies that have been spanning 30 years of development from early shuttle days and payloads all the way through stations existence. We've manufactured over 200 items on space station, many of them for use on station, and then others that were brought back to Earth for testing and verification for processes that would eventually be industrialized, meaning large-scale production and return to Earth. So we are working on technologies that are both for use in space and for return to Earth. This includes from plastics, ceramics, crystal, biological materials and tissue growth, as well as agriculture. We have a garden on the station. So we have a tremendous amount of experience and enthusiasm for this area. Finally, I'll just mention Archinaut 1, or OSAM 2, is a flagship program at Redwire that we are doing with NASA's STMD, where we are actually going to manufacture part of a satellite in orbit, and I can talk more about that, but it's an exciting transition. And to what Karl said, not only in the 50s, but I'm old enough to remember the 80s, where the promise of regular access to space and assembling the architectures after Apollo and such were expected and were the norm. And I believe we're finally getting to that point here now. So very excited to be here and having this discussion. Thanks.
Thank you, Al. And our fourth panelist is Debbie Tomek from NASA.
Thanks. Hi, everybody. Thanks for having us today. I'm pretty thrilled to be here, and especially with my colleagues, because I talk to these folks a lot. around ISAM, but ISAM and what it can enable for us in space infrastructure. So my role at NASA headquarters is a senior advisor focused on ISAM, space infrastructure and logistics, but also kind of spanning what it is ISAM can enable in our space architecture going forward. One of the colleagues already mentioned how disruptive ISAM can be, and I'll foot stomp that one, because when you start thinking, I joke, many of you have heard me say this a gazillion times already, but we can't think any other way with design other than the size of a payload fairing, right? So I joke around that our brains are the shape of a payload fairing size. Everything we've designed up to this point has been what can fit within a payload fairing. What if we said that these technologies could take that away, right? We can start designing architecture up there, not constrained by mass or volume, that we can assemble up there, we can manufacture up there. And what does that mean for sustainability? I mean, you start thinking about what it is we can do up there when these technologies are realized, and they are realized, they're happening. My colleagues here are proving this out in space, but I get pretty excited when I start thinking about what space infrastructure, logistics, and what that means to space sustainability. We essentially become what I like to call space urban planners, right? We start thinking about what it is we need out there to aid missions, right? We move away from that paradigm of a mission all on its own, taking everything that you need up there to do whatever it is you need, to infrastructure-aided missions. We've got the fuel up there because of folks like OrbitFab, right? We've got the servicing capabilities. It provides resilience. We've got tugs to maneuver without regret. So I'll cover a lot of this when we get to our slides, but thank you for hosting us, and I hope that by the end of this panel, you guys are thinking differently about how ISAM is a catalyst for sustainability and infrastructure. Thank you.
Thank you, Debbie. So you've heard a bit of what ISAM includes. There are a suite of capabilities that really are exciting for the next 7 to 15 years on orbit, on the lunar surface, and even for Mars exploration. And these capabilities are what we are looking to elevate. And the panelists are going to go through some slides, some of their introductions in depth. But before we do that, I want to highlight that this in-space servicing, assembly, and manufacturing national strategy that was developed as a U.S. government effort, and actually with some input from the private sector, resulted in 6 goals. The first goal was around R&D. How do we advance R&D for these capabilities? The second was around prioritizing, expanding scalable infrastructure in space, as you heard some of my colleagues mention here. The third was around accelerating development within the commercial sector, sending a clear demand signal. How do we do that within the government? The fourth was around international collaboration and cooperation. How do we ensure that public and private U.S. players do have the tools and the partnerships that they need internationally? The fifth is around sustainability. How do we ensure that we continue to make space sustainable using ISAM capabilities? And the sixth is on inspiring the next generation and ensuring that we are using all our tools within the government, within industry, to train the next generation of ISAM leaders, as we have here on the stage. How do you train a mechanical engineer, also in robotics and in spacecraft development, so that those skills, that multidisciplinary skill set, is available? So I will start with one question for each panelist, and as I ask you this question, then I would appreciate an introduction of your company and the work that you are doing. I'll begin with Al at Redwire. So if you could have the Redwire slides up, that would be great. Thank you. So, we talk about orbital persistent platforms, which can provide necessary infrastructure in space to prove out multiple ISAM technologies. What would help close the business case for commercial providers, and how will in-space manufacturing really help us achieve these platforms? Over to you, Al.
Right. So ISAM, you'll hear a lot about ISAM, but ISAM on its own isn't the end. That is just a tool to enable what our missions or visions, ultimate objectives are. So one of the things, as I mentioned, Redwire is focused on is the broad spectrum of in-space assembly and manufacturing and servicing, which includes large-scale deployments. And the rollout solar array is one of the products that we delivered for our prime Boeing and to the ISS. It was folded up in the trunk of a Dragon, and that is one of the realities that Debbie talked about, is that we all have to build for the purpose of launching, and then rolled out to deploy 50 kilowatts across two solar arrays. That is the reality of how things are done right now. As the spectrum of in-space manufacturing allows us to start thinking about how do we design and build to optimize for the operational environment, meaning that there are raw materials, there's feedstock, there's reservoirs of materials that are first taken up as commodities, and then the design and construction of the end product is never seen even 1G, let alone the environments of a launch vehicle, which are some of the most rigorous requirements to meet in design. So having manufactured over 200 items in low Earth orbit is this foundation of technology that promises to feed into the designs of the future. Not only are these manufactured, but there are facilities that are resident on ISS that allow us to just change out, let me say, print cartridges without changing out the full controls and monitoring for this manufacturing processes. So we've had years of that experience now on ISS that's going to translate to the private habitats and then ultimately to large-scale industrial manufacturing and the construction of platforms, persistent platforms and human-tended platforms. Let's see, this is an example, astronaut having printed a design that was uploaded from the ground. This is a pneumatic valve, and then assembling the valve, and then demonstrating the valve operating in orbit. Again, this, the motto of "make it, don't take it" is what we subscribe to, and as needed, components and parts that are rudimentary don't have to be taken up, but can be manufactured in orbit for the purpose of use in orbit. Archinaut 1, which I mentioned, is now being built and will be launched in a year or so. And this is a demonstration of in vacuum, in outer space, manufacturing a key structure. And this is a 10-meter boom that's being manufactured and will be demonstrated here out of a facility. And once that's manufactured, it's going to be rotated and relocated to manufacture a second 6-meter truss structure. This is just an example of how we can start to think about designing and building architectures of the future, enabling them to not have to survive launch, but actually be optimized for the operational environment that it will ultimately reside in. This is an example of where you can have that boom actually deploy a solar array, a flexible sheet solar array, very much like the rollout solar array I showed at the beginning, without having to go through a pre-built, rolled up, held down, and survive launch loads, acoustic loads type of environment. So the truss here is part of the demonstration that this will include is the metrology that goes along with the manufacturing. And here it's going to show the reorientation of the manufacturing payload in order to start a second truss structure. Again, this is going to the idea that ISAM is part of the solution and not the end product for this mission. In this case, we're building a boom structure that could be used as a payload for interferometry or for other operations. And what we'll do is after this construction, conduct the metrology that is required to then verify the performance of the manufacturing process. There are concepts for possibly then repurposing this payload for other missions, meaning that you can relocate the payload from this spacecraft to another. Persistent platforms are then enabled, meaning that very much like Space Station was done at the national level, the idea of building and operating persistent platforms, very similar to how cell towers are used right now, or other terrestrial infrastructure with shared services, power and data and thermal all provided as a common good for the benefit and economic benefit for multiple payloads is all being worked on, and I think was the promise of the early visionaries for space, and is now at the cusp of being implemented. Many of you have probably seen the concept for the future space telescopes, what can be done with in-space assembly and servicing, and this concept was put out by a team that for ISAT, commissioned by Paul Hertz at NASA, SMD, and the vision of what is enabled when you optimize for space can be seen here. There is regulation and policy that goes along with this, and it's critically important. Critically important not only for safety and the good of all, but also to enable and propel the business case for many companies that are looking at this, and meaning that investors want to know that there's authorization, there's a regulation, and there's expectation for a sustainable business practice. Finally, as I was talking to Debbie earlier about this, the architecture for the lunar surface is yet to be deployed and developed. This is a prime opportunity to integrate a sustainable future using ISAM for lunar architecture. Excited about that, and especially the day before International Moon Day. So happy International Moon Day. Thank you.
Thanks, Al. Now, we'll move over to NASA and ask Debbie if you could bring up the NASA charts, please, about space sustainability, which is something that is important to the public, and that it's also a topic this administration supports in our space priorities framework. Now, can you tell us how we can use ISAM capabilities to mitigate long-lived debris and just work towards achieving space sustainability?
I can. Really good question. And I'll hit that through the course of these slides. So I do want to, because I think sometimes folks think, well, ISAM, what does that mean to active debris remediation or orbital debris? And hopefully I'll walk you through that with these charts, as well as give you a broader perspective on what ISAM, as I had said, those capabilities fully realized, what that can enable for space infrastructure and giving us the sustainability that Al has been talking about. The first chart, I kind of touched on this when I spoke earlier, but I want you guys to really kind of pull deep on your vision and think about a future in which we have the kind of technologies that can enable all of these different things, right? The logistics, the interoperability, us starting to think about how it is that we want to operate in space, much the same way that you either drove here, you flew here, right? None of us like to think about infrastructure, the sustainability of that infrastructure until something goes wrong, right? It works for us, it's there. Well, we want to have that in space, because that's what's going to give us that sustainable presence out there that we want for humans and for robotics that Al touched on, right? We don't want to just go to the moon, take a selfie, and turn around and leave, right? We want to be able to go there, do science, and Mars forward, right? We want to explore. We're finding more and more things now. You guys saw the James Webb and what we're discovering out there, and we're going to want to continue to explore. So I want you to imagine that future, but I also want you to think about the best way is sometimes to think about it is think about how we have done that as a nation, as humankind before, right? We've got the Transcontinental Railroad that opened up the whole nation for us. We've got the interstate highway system. So think about, again, broader what it is we need to enable sustainability, whether it is a sustainable presence, whether it's technologies to clean our orbits up from orbital debris. And so what would be the steps for that? We've been working on a concept called the Space Superhighway. Many of you have heard about it before. I don't want you to get distracted by that term as much as thinking about it in principle, thinking about what it is we need logistics-wise out there. When you start thinking about, that's why I gave you the examples of how we do it terrestrial, right? When you think about a highway and driving from here into the airport, and if your car breaks down, right, we can call the AAA. You've got a tow truck, right? You've got the ability to take it somewhere. You can get it serviced. You can get it repaired. You can swap out a battery. So all these things that we are very used to having here Earth-based, we want that same kind of system up there in space. But what do we need to do that, right? It means that we need to continue to work and advance these technologies. We need to work with our commercial partners. We're seeing the fantastic things that they're demonstrating. I love the video that Al shared because I think about that, right? It's a robotic arm out there. We're assembling solar arrays out there, right? Think about how far that's going to take us. So when you start thinking about ISAM enabling sustainable space infrastructure, and this is an eye chart, so I don't feel like you have to read everything in there, but this one is particularly a good chart because it really, this and the last couple charts I have summarize all of those different capabilities that we can have out there no matter what the orbit is. You start thinking at it, Ezinne asked me a question about how this can enable ADR and orbital debris and remediation. These types of technologies, whether it be rendezvous proximity ops, whether it be the robotic arms that can grapple, it's learning how to actually design spacecraft so that it is sustainable to begin with. When we start looking at servicing and repair, how can we make sure we have spacecraft prepped so that going forward, if something happens, we can go up there and grapple it. So I know we all talk about the AAA in space, but we're kind of not kidding, right? Can we actually have that? But we also need to be able to think about how we can quickly get up there and have quick response. ISAM capabilities, whether it be like I said, the robotic arms, the grappling, the RPOC. There's all types of technologies, again, that are deriving out of ISAM. And ISAM, as Al has mentioned, isn't everything we need up there, right? But it is a massive catalyst to enable this infrastructure going forward. So not only does it give us the ability to enhance in active debris removal type of techniques, but it also gives us the ability to service out there. It provides for us not only the resilience that our defense partners need, but it gives us the capability to service things that we have out there, whether it be on the lunar surface. When Al mentioned that we were talking, right, we've got to start thinking about, okay, we're up there, we're on the moon, now what? Right? Well, I've got a lunar terrain vehicle that needs a battery pack swapped out, right? I've got filters I need to switch out on the habitat, right? There's all these types of things where we've got to develop, whether it's supervised autonomy robotics or whether it's fully autonomy robotics, to be able to go up there and do these things themselves. And ISAM capabilities open up that trade space. These last couple slides, this one I know is another eye chart, but it's one of my favorite because it breaks down on the left the key ISAM capabilities, right, in the icons, right? We've got the robotic manipulation, the rendezvous prox ops, relocation plan servicing. These are all capabilities enabled that lead us to the sustainable framework. Whether we are retrieving debris up there that's not supposed to be up there, whether we're capturing that debris and repurposing it, whether we're capturing that debris and bringing it back in a controlled entry because it's something that we want to keep, or whether we're just throwing it into a self-cleaning orbit so that it can eventually deorbit and burn up on reentry. All of these not only supporting ADR, but they support really four big objectives now at NASA: transportation, habitation, infrastructure, operations, and science. So that's the beauty of ISAM technology, right? Again, it's not the cure-all for everything, but it crosses over all of our portfolios, right? Like I'd said, whether it's swapping out a battery on the lunar surface, whether it's servicing a space telescope out in L2, eventually assembling it down the road, right? We've got a ways to go for that, but we'll eventually get there with that. But right now, focusing on the orbits, cislunar, GEO, LEO, right? What it is that we need out there to provide, as I said earlier, infrastructure-aided emissions that lead us towards that sustainability piece that's so important to us. My last slide here, again, it's a sample of capabilities enabled by ISAM, but I wanted to lay it out so you could see when I talked about the cross-cutting nature of this between civil, commercial, and defense, right? How this benefits. And this is why the work that Ezinne is doing at OSTP is so important, because she's really hurting all of us in the government to start thinking about how it is we can advance these capabilities, right? The strategy has been released. We're all now working on an implementation plan, but how it is that we can engage and leverage commercial and academia to actually do this, right? We move to this type of model. This isn't the government, it's not NASA owning all of this. It's us providing a demand signal because we want to be able to buy these services for us. It's moving us towards an infrastructure as a service type of model, and ISAM can enable that, hence leading us to the sustainable presence that I know if you're here, you're somebody that desires that also. That's my last chart, Ezinne. Thank you.
Thank you. Thank you, Debbie. I think you've seen from Redwire and NASA that there are numerous servicing capabilities. And so I'll turn to OrbitFab and come back to Jeremy and ask, when we think of some of the services we've seen, commoditized, autonomy, refueling, tugs, which of these services should be implemented within the next 5 years and why? Because we can't do everything at the same time. So what should we start with?
Agreed. And I want to go back to Debbie's slides here where, she likened the space industry to the Industrial Revolution. But the number one single cause for why we have everything we have today is fuel. We had fuel to move goods and services from one place to another, fuel to give energy to power plants. Fuel drives our global economy. We have no fuel in space, which is why there's no in-space economy. We talked about having, a space highway going from Earth to the moon. Your highways are not going to be built with roads in space. They're going to follow the depots that give your ship or your asset the fuel to get to where you want to go. Whether that be Mars, whether that be the asteroid belt, whether that be the moon, you're going to follow where the fuel is, because that's going to be our concept of what a freeway is in space. And so, going back to your question, it should be done. The refueling is paramount, because if you want to do in-space servicing or active debris removal or in-space manufacturing, the costs dramatically come down when you can refuel those assets to keep using them. If you want to do active debris removal right now, depending on the size of the object you remove, you can do between 1 to 3 debris removals. If you can refuel that asset, you can do between 9, 12, and eventually even 100, get to hundreds once the technology gets there. But in order to hit that first step to make things economically viable for our customers, you have to do refueling. Now, that being said, if you want to do, we need to do active debris removal now. We need to do tugs now, because everyone needs to start with their minimal viable product, especially on the commercial side. And those ones are not going to be reusable, right? You're gonna put it up, you're gonna test out the technology, and then from there you're going to build your next gen capable asset. Look at Northrop Grumman's MEV. They had their initial dock out in the geo graveyard, and then they had their MEV2, which actually docked to the Intelsat satellite as it was still broadcasting. But those are still disposable, right? So in my architecture, they use them 3 times, and then they have to throw them out. But those assets can still be used. The technology there is still good, but they're just not designed for refueling. And so, I don't know how much I should harp on this topic. But if we want a truly in-space economy, which doesn't count geocom satellites, does not count Earth observation, because all of those are for benefiting terrestrial uses. So that's the space economy, but the in-space economy is what we all want up here. In-space manufacturing for goods being built in space, commercial space stations for people to go and visit, for tourism. Everything that we want to see is what we're striving for. But today, the only in-space economy we have would be the International Space Station and Northrop Grumman's MEV vehicle. So everything needs to be done to now, but the focus really should be nailing the refueling portion first while we work on everything else.
Thank you, Jeremy. If you could pull up the Air Force slides, I'll go to Karl now. And we just heard from Jeremy that we need modular, reconfigurable space system architectures in order to have longevity in space. And as we look at the return on investment of some of these capabilities, like refueling and how it would extend, the operational lifetime of missions, what capabilities, whether it's servicing, like Jeremy talked about, or manufacturing, like Al talked about, or even assembly, are relevant to the Air Force within the next, say, budget cycles? What are they looking for?
So if you talk to any military historian, they will tell you two things they get really excited about are logistics and the ability to move. And you can't have maneuver without a logistics chain. You can't support maneuver without refueling. And I think that refueling is actually really exciting because it is well underway. Companies like Jeremy and OrbitFab are working towards commercial solutions, and we are committed to trying to purchase as many commercial services rather than standing up a program of record and spending a lot of money to try to duplicate what the commercial industry has already done. So one of the things that I've started to do is work towards, okay, what's next? And servicing is a little complicated in the sense that if you look at tier 0 here, this is life extension of things that are already up there. And so, Jeremy brought up MEV. There's the DARPA RSGS mission, OSAM-1. They're up there to service what I call legacy spacecraft. Tier 1 right there is the maneuver without regret. That is the ability to maneuver a satellite anytime for any reason without having to worry about decreasing its lifespan. And you only get that through refueling. Tier 2 is the replenishment and refurbishment. And what I mean by that is this is the blurring that comes in when you say servicing. If we can't do refueling, then a logistics chain collapses. It doesn't exist. If we can't do refueling, lots of other things collapse. But by being able to do refueling, the RPO, the docking, you're going to be able to enable the skill set that you need to do all these other things. So what we started looking at is what's next. And if you look at just the life limiters on spacecraft, okay, fuel is number one. So I'm going to say that fuel in a couple of years is going to be a solved problem. The next thing is electronics. The space environment is a really horrible environment to stick electronics up there. We are working with computer architectures that were designed in the 1990s. We are writing software to try to fit onto those processors, yet we were talking about in one of the earlier panels about autonomy and the need for increased computing capability. So my goal would be the next thing is to be able to repair, replace, and upgrade a computer on orbit. So if you start talking about one of the reasons why we have the compute architectures we do is they have to live and survive in a radiation environment for 15 years. If that computer only has to survive for 2 years because I can replace it on a 12-month cycle, then that opens up a lot of possibilities for computing, for software, and not just the ability to replace, but again, upgrade. And then the next thing, the next life limiter on satellites is power systems. And 50% of that is just degradation of solar panels. Al showed the video of unrolling a new rollout array on ISS over the old arrays. Imagine if you didn't have the old arrays sitting there anymore. So the ability to modularize not just the computer, but solar arrays, I think is a really powerful construct. So it's what we're interested in the short term is what are the things that we need to do now to start designing the spacecraft of the future? Because if we can't do these things, if we can't make these pieces parts work, then the dream of the space superhighway falls apart. If we can't do refueling, the dream of the space superhighway falls apart. So what we're interested in are what are the practical applications that we can start doing right now that require us to rethink how we design spacecraft, and then what skill set do we need to do that?
Thank you, Karl. I want to pull on one of those threads and ask the other panelists. Karl has just given us a bit of a roadmap for the Air Force, and even Jeremy, emphasized the importance of refueling. But what other roadmaps are there? and I'll open this up to everyone. So what do you see happening first and second and third?
Well, I'll say, I mean, Karl clearly is you know, in the national security kind of focus and motivation. There is definitely roadmaps for profit-making companies, and I think that's part of the motivation and incentive here that we have to recognize. And probably some of the early adopters is businesses that see the profit potential. I was fortunate to work in the geocomsat business for a few decades. Technologies were adopted there and deployed most frequently when they can get a business advantage in deploying their payloads. I think that's what we'll see with adoption of ISAM is you know, the platforms that can provide a startup or an existing business with an economic advantage will get adopted quickly and deployed and proliferate quickly. I can give you two examples, quick examples. Lithium-ion batteries on geocomsats were, you know, shunned until one operator decided that they can increase their payload capacity, and then all of a sudden, all operators had to have that. Those are the kind of adoptions that I think will accelerate, you know, ISAM integration into architectures.
Thank you. Anyone else?
Yeah, I mean, one alternative path would be having, you know, U.S. government or any government advocate for commercial industry to start flying simple servicing components like a docking plate for deorbiting, whether that be you know, OneWeb's using the Altius docking plate, Altius Astroscale docking plate. That's a great example of a very low risk adaptation for a servicing vehicle to go and perform a deorbit maneuver in the future versus having to grapple with a piece of debris or a dead satellite that doesn't have that. You also have you know, refueling interfaces, you know, slightly more complex, but still lower on the NRE needed to integrate that into a vehicle, as well as like power and data connectors. So having, you know, groups like ComFERS, U.S. government or the DoD to promote these serviceable interfaces will go a long way into adding into a quicker adoption for the industry.
Well, and I'll even turn that around and throw it back in Jeremy's lap a little bit. Yeah, the U.S. government is all about making sure that we're adopting these standards, but there are a lot of people that say, well, the U.S. government should be responsible for developing these standards. No, we should not. I think history has proved time and time again that the U.S. government should not be in that business. There's a lot of rather dramatic failures over time. But if you start looking at ComFERS and you start looking at commercial capability, Lockheed Martin's announcement, I think a little over a year ago, about making the A2100 buses refuelable, they're going to start putting a port on that bus as a standard feature. And if you want that not on your bus, that's actually going to cost you more than just buying it with that feature on it. So I think it's really important that industry really lean into this. The U.S. government, at least from the DoD perspective, is here to support just that. And if you see anything that's come out of the orbital prime stuff, any of the announcements that are starting to come out of Los Angeles, you see you know, support for commercial development of these capabilities.
Thank you. Debbie?
I agree with all the comments on my colleagues, especially the fact that government does not need to be developing and owning standards. I'll foot stomp that one. But we certainly do need to be looking at how we can advocate for the adoption of these standards. We've got to start looking at the rules of the road per se and the norms of behavior. And as NASA, I feel like we have a unique opportunity to demonstrate as a civil agency what these norms of behavior and what these standards are. But I think encouraging commercial sector to adopt these standards and we can perhaps be out front in showing how that can be done is what's important, whether it's providing incentives to prep spacecraft, supporting and working with ComFERS and different organizations like that and the development of these standards, again, so we can get ourselves down the road and we've got these common interfaces, much like we'll go to a gas station now and we all know what kind of pump to pick up, because our car has been designed, right? And so we want to get to that point in space, whether it's a plug and play on a persistent platform where we've got utilities and payloads, and we can go up there and put a new instrument up, and we can replace COM and GEO spacecraft every 18 months. So again, it's moving us to adopting slowly. I hope quicker, not slowly. It's moving slow now, but we hope that it's going to move more forward as these ISAM technologies mature. So we're at an interesting cusp in time. Thank you.
Thank you. So you heard it here first. ISAM is really exciting. They're going to do all of it at the same time. And in a few years, we will have refueling, we will have in-space manufacturing, we will have lots of debris mitigation technologies in the works. So I would like to turn it over to you to ask any questions of our panelists. Are there any questions in the audience at this time?
No need to be shy.
Yeah, these panels are usually pretty talkative.
It looks like
Okay,
there is one.
I have one. Mic's working? Okay. So in terms of the in-space manufacturing, how much of that is kind of, I guess, is it really just all going to be kind of service-based? Like if I say, oh, I want to 3D print something in space, can I just call you guys up and say, hey, can you go print this part for me? Or is it really all going to be kind of, contracted as, well, we are going to build these big space structures and we have the tech to do it, so it's really just for us?
Yeah, good question. I think that a lot of the technologies will become adopted kind of fundamental building blocks for the industry. So right now, yes, there are some scenarios where you might imagine 100-meter antennas being manufactured and delivered on orbit by a manufacturing facility. And these concepts aren't that far off. There are some people, including AFRL, that are looking at how do you do 100-meter class, kilometer class kind of structures in space. But there's other technologies which I believe are going to become ubiquitous quickly, which are deployed at prime facilities and space structures, manufacturing facilities that will include ground built and then deployed and launched and then in space manufactured, and it'll just be integrated technology into the platforms, which is very, very feasible. These are, the price points that we're heading to here are proportional to the spacecraft costs that exist right now.
Al, this question's for you also. Really enjoyed the videos and the animations. Question on the parts that have been built in space. Do you have a good understanding of the mechanical, structural strength characteristics of how they match up versus something that's manufactured in 1G on Earth?
Yeah, very, very good question. I still remember the early days of 3D printing terrestrially, and the same questions existed then, right? So yes, the potential to not only manufacture in space but bring them back to Earth to do the testing has been used repeatedly. So we have done the testing, destructive testing to see the consistency and the true strength. Not just in traditional materials, but we've also done it with regolith simulant and brought back for demonstration of structures made out of lunar regolith. So yes, the answer is we do have that data, and working with NASA and our commercial industry sponsors. By the way, the opportunity to integrate commercial industry in with their R&D on the space station exists, and that's one thing that we've had the opportunity to do. Even Lowe's home improvement has been part of that industry. So the answer to your question is, yeah, we do that testing and we do the engineering around that, including how do you scale it to get industrial scale production of some of the materials.
Thank you.
Yes.
Okay, thank you. First of all, great discussion and presentation. This is a really exciting area for a lot of us, and it's good to see the energy and the enthusiasm. I've got two questions, and I'll just limit it to one. So have we done any additive manufacturing with metallics in space to this point, and kind of where are we on that evolution?
So I'll answer that. That has not been the focus for a few reasons, but that is on our roadmap. So that I'll answer it that way. The technology exists; it just hasn't been the priority right to this point.
And kind of a slight follow-up is not this orbital debris a source of material to do that? Is that kind of in the thinking somewhere?
Well, okay, so when people talk about in situ resources, I include man-made resources up there.
Okay.
But I think one of the reasons is we started looking into the metallics. Number one, you have a power issue. Number two, you have a thermal issue. Mm-hmm. I think one of the things that's been tossed around in my brain for quite a while is, and it was actually spawned by seeing yield to torque 3D printed plastic wrenches. So the idea of instead of printing essentially eternal things up there, can you print one-time use only? If you look at RSGS or OSAM-1, they're taking up huge tool sets with them to be able to accomplish their mission. Some of those tools are one-time use only. Could those be printed on orbit? And then that leads me to a line of thinking of, shouldn't we be printing those out of materials that are easier to reuse? So start looking at things like, PEEK, some of the polymers, low CTE materials. We immediately, as engineers, we jump into metallics, but that's not necessarily thinking far enough down the road. But yeah, in theory, someday you'd be able to reuse that material on orbit.
Yeah, and I would add that with orbital debris and repurposing and reusing what's already in orbit, it's a technology that still requires more assessments and studies. We're just not at that point yet.
Let me just say I really like the idea, and I think that should be one of the aspects of orbital debris remediation is repurposing.
Yeah.
I'll just throw that out there for any entrepreneurs.
Yeah, and I'll agree with that one also. And if you really start, again, back to the long-term vision, we want to get to the point, as Ezinne had said, that we do repurpose what's up there, right? There's a lot of valuable materials on orbit, and we don't always just want to grapple it and toss it into a self-cleaning orbit, right? We want to be able to take it, repurpose it, use it for something else. And so as part of a roadmap or long-term vision, we'd like to get to that point where we can consider it in space ISRU and leverage what's already up there.
Okay, thank you.
Thank you. We have one question over here.
Yeah, this question comes from our online audience, Dan Dumbacher from AIAA. He's speaking of entrepreneurs. How is the private capital market supporting or reacting to the ISAM market and its opportunities?
Yeah, so the capital market was acting really great up until a few months ago, for obvious reasons. But there's still a lot of excitement in regards to what the ISAM community is doing and the economics behind it. So with the right business models, I mean, you can still raise money even in this environment as an entrepreneur. I mean, we're doing that as well, raising our A round, and some of the best companies are forged during downturns. So I mean, I'm not. I think if you're just starting a company now, have a really solid business model and pitch when you're going to see investors. But I don't think that even in this recession that the capital flowing into space companies and ISAM companies will stop.
Let me add that, as I mentioned, Redwire was formed over the last couple of years through the acquisition of 8 companies, initiated by Aero Equity Industrial Partners, a private equity firm, who is still, publicly stating very bullish and forward-leaning on acquisitions of, in revenue and profitable companies. So there's still very much an interest, and to the comment. There might be a lot of froth that's moved out of the way, but there are a lot of value purchases still going on.
Yeah, and I mean, from my perspective, what I've seen is there's a lot more private capital out there than there is U.S. government dollars to be invested in this. So my mantra, and Jeremy's heard me say this many, many times, where can my one U.S. government dollar go to accelerate the 10 or 20 or 30 commercial dollars that are sitting out there? And we're still seeing some of that. Although I will throw this out there, and I mean, this is coming from me, who's a big engineering nerd. I love the technology. But I think one of the things that you have to ask yourself, and you have to be able to answer really quickly, because this is very squarely push technology. We are trying to push these things into a system that is not keen on change. How does my technology benefit the future? And if you can't answer that question in 10 or 15 seconds, then you're dead. 3D printing is great. Why do I care? Refueling is great. Why do I care?
I'll add to that too. I think a lot of the burden falls on us and the government to provide the proper demand signal. So it is us deciding, okay, that we know that we're going to need this capability or this technology. I'm going to want to have my spacecraft serviced. I want to be able to leverage an mission extension vehicle, an MEV, for this. And it's, for NASA, right? It's us slowly moving away from having to gold plate every single spacecraft and mission. So we'll obviously always have our exquisite ones like the James Webb, right? It's a fantastic what we're seeing come out of that. But we want to get to the point that again, we can get up there in a quick cadence and advanced technologies and have missions that I don't have to spend tons of money on gold plating, because I know that we can get up there and service and repair once we're on orbit. But a lot of that is sending that demand signal that those are the types of services we want, that we're going to want to buy fuel from the OrbitFabs. We're going to need some of the technology to manufacture on the surface of the moon from the Redwires and from the Maiden Space Company. So it's the burden is on us to do that within the ISAM strategy. Ezinne is having us address that and think through how we can get coordinated across the government and sending a consistent and strong demand signal on how we're going to use these. But we've got some runway ahead of us, but we're making progress.
I hope this has been helpful in at least understanding the landscape as it stands today and ISAM and what's going on within the government and some of our major stakeholders on the private side as well. And I want to thank AAS and the symposium for holding this session. Thank you.
Thank you, Ezinne. Yeah, I think this was a real super a panel. I took a few things away on making products and making the space superhighway. I really enjoyed the comments regarding government should not make standards for the industry, which I thought was great. And literally, I did have a question, and as I was coming up, y'all answered it right towards the end, which really came down to, okay, my government colleagues, this is great. So when are you going to start pushing on that being a requirement? And Deb, you put that right at the end. It was great. I'm like, how apropos is that? I don't even have to ask the question. I just kind of give a little mental telepathy. Go ahead.
I'll actually answer that in the next month or two. You will see the announcement of a Space Force spacecraft that actually has cooperative refueling port on it with the intention of refueling in an orbit in the next couple of years.
That's awesome. I think that's a big deal.
And if you look at your European partners as well, with their ADR, they're also adding refueling there. So it's not just the U.S., it is globally. People are seeing the value in ISAM efforts.
Right, for sure. I mean, that is one of those things. We can all come up with these great texts and be ready to do it and answer the question of why is it important. But it really comes into the service providers starting to say, we're going to use this. Lockheed Martin saying, we're going to put this on. If you don't want it, that's fine. You have to pay us extra, but you're gonna have a refuel capability. I think that's super. So, panel, thank you very much. This was really, really great. So.